Hello everyone, welcome to the lecture series on the subject VLSI design. So basically here we are concentrating on the syllabus which has been prescribed by Vishwesvaraya Technological University Belagavi. Uh, in the previous module, that is module 2, we had discussed on different aspects such as how to draw a schematic for a design, how to draw the layout for that particular schematic which we had drawn for a particular design, and how to draw the stick diagrams. Later on we had discussed on sheet resistance and the capacitance which can occur uh, near the contacts, and then uh, in the metals and all those things. Okay, so in this module we shall proceed with the scaling of MOS devices. Okay, so what do you mean by scaling? Scaling is nothing but it is a proportional adjustment of the electronic devices while maintaining the electrical properties of the device. That means what scaling in the sense, and somewhere in 1965 Moore said that the number of transistor in a chip has to be doubled for by every 24 months or 18 months. Okay, that means what the number of transistors in the chip has to become twice the number of transistors which were earlier. That means in the other way, the size of the chip has to be reduced by half. Okay, so in order to achieve this Moore's law, people started using different technologies. As of now we are speaking in terms of what we are speaking in terms of we are telling okay, this is 180 nanometer technology, this is 90 nanometer technology. And what does this technology mean? Technology is nothing but what? Technology is nothing but the channel length what we are telling. Okay, now in order to achieve that, uh, Moore said that what every this thing has to be doubled for every 24 months. So it started with what? It started in terms of micrometers, and then they started reducing these channel lengths and then channel widths and all those things. Based on that, they have come up with different technologies. Now as you can see here, this is the image what you are having. This is of what? This is of 130 nanometer. Later on they have scaled down the transistor to 90 nanometer, and again they scaled down to what? To 65 nanometer, and again they scaled it down to what? 45 nanometer, 32 nanometer, 22 nanometer. Okay, as of now in present this thing, people are speaking in terms of what? In terms of 10 nanometer technology. As you can see the smartphones what you are having, like Snapdragon 720, Snapdragon 710, uh, all these have been using what? These have been using 10 nanometer technology. This thing, that means what? The channel length of a transistor is of 10 nanometer. Okay, so reducing these dimensions and then properties is nothing but scaling. That means we are scaling it down. Here as you can see, the scale is what? Here it is 130 nanometer, and here if you look at this is what? This is 22 nanometer technology. That means the length has been scaled down from 130 nanometer to 22 nanometer, but the electrical properties what you can say, or the voltage properties or current properties or the working principle of the MOSFET, it should not change, but the dimensions can be reduced. Okay, so what and all are the impacts by scaling down the device? What can I achieve? So minimum feature size, that means size will be reduced, the number of gates in a single chip will be increased, the power dissipation will be reduced, and we can achieve more frequency, and the die size can be reduced, and the production cost can be reduced. Here you can see as an example the same SRAM cell which was produced in 1980s and which was in terms of 1700 micrometer square, but whereas this might be an example for 22 nanometer SRAM cell where the whole this things area required to cover the thing what we had achieved in 1980 has been reduced so widely. See here in 1980s the area was 1700 micrometer square, but using 22 nanometer technology the same this thing has been achieved in terms of area 0.092 micrometer square. Okay, so what are these scaling factors? Okay, while we are scaling down the things, we are sure we want to make sure what we have to make sure that the electrical properties should not be changed. Okay, so based on this we are having different scaling factors. Those scaling factors are alpha and then beta. Okay, so alpha represents the scaling factor for linear dimensions. That means the dimensional properties like channel length and then width and all those things are in terms of linear things. So those factors have been scaled down in terms of alpha, but the voltage, supply voltage and then thickness or gate oxide thickness, those have been scaled in terms of what? In terms of beta. So let us look into different scaling factors or scaling parameters. So how scaling will affect those parameters that we will study. Okay, so we have to make sure that this alpha and beta what we are having, this alpha and beta are constants. Okay, so some numerical constant, but that numerical constant will depend on what type of technology you are going to use. So let us look at the first scaling factor, that is channel length. So when it comes to length is actually what? Length is actually the dimension of a MOSFET. Okay, so here you can see the MOSFET over here, right? Here you can see this thing. So it is what? It is the length, or here the channel length what we can see. So after scaling down, what might be the thing? So let us consider that our L dash is what? L dash is our scale down value, L is our before scaling down value. So alpha will be our parameter. So here what we can say, so this L dash is what? L dash is after scaling, and then this L will be before scaling. In the similar way we can go for channel width also, since width is also our dimension. So what we can tell that it is also will be scaled down by a factor of 1 by alpha. So gate area. So what is gate area? The gate area is what? Now if you look at the thing here, you can observe that this whole this thing what we can have a p substrate and thickness oxide and then this polysilicon, this whole represents what? It whole represents our gate area, and this is totally dependent on what is the as you can see, this might be looking something like a rectangle. If you want to find out the area of a rectangle, then what you will be doing, you will be multiplying length with the width, right? So as we all know length has been the scaling factor for length is what? It is 1 by alpha. The scaling factor for width is what? It is 1 by alpha. When it is going to be multiplied, the scaling factor for this thing will be what? It will be 1 by alpha square. So the scaling factor for gate area will be what? Gate area will be 1 by alpha square. Okay, so next, gate capacitance per unit area. Here one what we have to observe is that this is what? This is our CO, Okay, CO is given by what? CO is given by epsilon naught ox or epsilon naught divided by thickness. Okay, now per unit area, here what we can tell, that here area represents what? Per unit area, in the sense what? The area will become what? 1. Okay, and out of this, the gate capacitance is given by what? It is given by C naught is equal to epsilon naught by our thickness. Okay, now here what we can tell is that the thickness is what? It is given by scaled down by a factor of what? It will be scaled down by a factor of 1 by beta, but whereas epsilon naught remains what? It remains a constant. Okay, so what type of material you will be using? So based on the type of material, this epsilon naught will be a constant. So 1 divided by 1 by beta will be what? So area C naught, so that means gate capacitance per unit area scale down factor will be what? It is beta. Okay, so we will go on to the next thing. So gate capacitance, so gate capacitance represents this area where we can have this particular thing. So it is what? It is C naught into L into W, as we have know that the C naught scaling factor is beta, length is 1 by alpha, and then beta is what? It is 1 by alpha. Beta into 1 by alpha into 1 by alpha, that will give us what? Beta by alpha square. So the scaling factor for gate capacitance is what? It is beta by alpha square. Next, so carrier density in a channel. So carrier density is nothing but the average charge per unit area in the channel in on state. That means when the charge carrier will be, when they will be activated, the charge carrier will be activated when the MOSFET is in working condition, and that too the charges will be lying where? The charges will be lying near what? It will be lying near our channel length, so near to our gate. So what we can tell is that Q is given by what? Q is given by C into V. So here C represents what? Here C represents the capacitance of what? Our gate capacitance, and the voltage what will be applying, that will be what? That will be VGS. Now as we all know that the C naught scaling factor is beta, and we had said that supply voltages or any type of voltages, the scaling factor is what? The scaling factor is 1 by beta. So when you look at this, what will happen is that now beta into 1 by beta, so this beta and then this beta will be getting cancelled. So finally left out is what? Finally will be left out with 1. So the scaling factor of carrier density in a channel when the transistor is in on state, it is what? It is a numerical 1. So channel resistance, so the resistance offered during what? In the channel. So the equation is given by what? R on is equal to L into W Q 1 by Q on into mu. So as we all know, L scaling factor is 1 by alpha, width scaling factor is 1 by alpha, Q on is unity, and mu is a constant, where mu is what? Mu is the mobility of our charge carrier. Now 1 by alpha, again this what will happen? Again this will be cancelled down, again we will be left out with what? The scaling factor of channel resistance when the MOSFET is in on condition, it is what? It is 1. So gate delay, so gate delay is nothing but what? It is the delay which can offer through the channel. So gate delay is given by R on into Cg. As we all know, R on is scaled down by a factor of 1, and Cg will be scaled down by a factor of beta into alpha square, beta by alpha square. So the channel density, the scaling factor for gate delay will be beta by alpha square. Now for IDS, so saturation current, most of the transistors what we are using, those will be working in terms of what? In terms of saturation region. Now coming to the equation of saturation region, what we are having, the saturation current will be given by C naught mu by 2 W by L VGS minus VT whole square. Now when it comes to this thing, C naught we know, W we know, scaling factor of a C naught we know, W we know, L we know, VGS minus VT we know. And then now here if you look at this, okay, as of now here you are having this we know 1 by alpha and this we know 1 by alpha. Now if you look at this, VGS is scaled down by a factor of what? It is 1 by beta, and again here it is given by a factor of 1 by beta. So VGS by, so it will be what? It will be VGS by beta, and then again it is VGS by beta. So VGS minus VT whole this thing divided by beta. So since it is a whole square, the scale down factor will be what? It is 1 by beta square. Now this 1 by alpha and 1 by alpha will be scratched down. So this beta and then this beta will be gone. So finally we will be left out with what? We will be left out with 1 by beta. So the scaling factor of saturation current is given by what? It is given by 1 by beta. Now current density is given by the saturation current divided by area. So as of now area we know it is 1 by alpha square, and then this is 1 by beta. So alpha square will be going up and then beta will be coming down. So the scaling factor of current density will be alpha square by beta. Switching energy, so this is given by what? It is given by Cg by 2 into VDD whole square. As we all know, VDD or any supply voltage, it is 1 by beta. Cg also we know it is given by beta by alpha square. Now if you look at this, now what will happen? Now Cg is what? Beta by alpha square and then 1 by beta square. This beta and then this beta will be cancelled down. So finally we are left out with what? 1 divided by alpha square beta. So the scaling factor for switching energy per gate is what? It is 1 by alpha square beta. Moving on to next thing, power dissipation. So power dissipation per unit area is given by Pg divided by Ag. So again we know that Pg is given by 1 by beta square, Ag is given by 1 by alpha square. So alpha square 1 by alpha square, in the sense alpha square will be going up and then beta square will be coming down. So the scaling factor for power dissipation per unit area will be what? It will be alpha square by beta square. Moving on to next slide. So power speed product, this can be given by what? This can be given in terms of Pg into Td. So Td is what? So Td is power dissipation per gate. So Pg is power dissipation per gate area, and then Td is delay. Okay. So Pg we know it has been scaled down by a factor of 1 by beta square. So Td is scaled down by a factor of 1 by beta. So this beta and then this beta will get cancelled. So we are left out with what? We have been left out with 1 divided by alpha square into beta. So coming to the summary of scaling effects, if you know these things, so any supply voltages will be scaled down by a factor of 1 by beta. Any dimensions will be scaled down by a factor of 1 by alpha. As we all know, supply voltage 1 by beta, okay, and then channel length 1 by alpha, channel width 1 by alpha, gate oxide 1 by beta, Ag gate area, it is length into width, so that's why it is 1 by alpha square. C naught is what? It is by beta. Gate capacitance, it is beta by alpha square, and then carrier density, it is 1, channel resistance is 1, saturation current is 1 by beta, and then current density is alpha square by beta, and then power dissipation per unit area is alpha square by beta square, and then power speed product is what? It is 1 by alpha square into beta. So these are the things what we should consider when we are scaling down. So simply we cannot scale down only one parameter. If you are going to scale down any device, then we have to look into all these things which will be affected. So if you are changing, if you are shifting from 180 nanometer to 90 nanometer technology, at that time these all the things what these parameters are there, those will be scaled down. Now VDD, scaling down of VDD in the sense what? Scaling down of VDD is nothing but supply voltage. In 180 nanometer it might be working in terms of 2 volt, but when you are scaling down it to 90 nanometer technology, then it will be what? It might be working in terms of 1.2 volt. So in the similar way, channel length has been reduced in terms of what? Channel length has been reduced in terms of from 180 nanometer to 90 nanometer technology. So these are the scaling factors which we need to consider. In the next class, we shall discuss on what? We shall discuss on the subsystem design. So what are the factors which we need to be considered when we are designing any product? Okay, thank you.